Scene script. Have you ever wondered if we could travel to distant galaxies in a fraction of a second? Imagine, if you will, a universe where the vast expanses of space don't matter. A universe where you could hop from one galaxy to another as easily as crossing the street. Sounds like pure science fiction, doesn't it? But what if it's not? What if there's a theoretical solution to this cosmic conundrum? A concept that challenges our understanding of the universe and opens up infinite possibilities. It's a concept that has fascinated scientists and science fiction writers alike for decades. A concept that could potentially enable faster-than-light travel, making intergalactic exploration a reality. This concept, this key to unlocking the mysteries of the universe, is nestled within the realm of theoretical physics. It's a concept that could transform our understanding of space and time. What if I told you science has a term for this hypothetical shortcut? It's called a wormhole. So, what is a wormhole exactly? Well, let's simplify it. Imagine you're holding a piece of paper. On one side, you mark a point A, and on the other side, a point B. Now, in a conventional sense, to get from A to B, you'd have to travel across the surface of the paper. But what if we could fold the paper, bringing A and B together? That's the rudimentary concept of a wormhole. In the grand cosmic context, a wormhole is a theoretical passage or shortcut through the fabric of space-time, a concept that Einstein's theory of general relativity allows. Picture space-time as a vast cosmic sheet. Now, similar to our paper analogy, if we could fold that sheet, connecting two distant points, we'd have an essence of a wormhole. However, remember that we're not merely dealing with a two-dimensional paper, but a four-dimensional reality, 3 dimensions of space and 1 of time. Our wormhole isn't just a tunnel, it's a tunnel through time as well as space. So, if you were to traverse this tunnel, you'd technically be moving through space-time itself. Now you might wonder, why call it a wormhole? Well, the name is quite illustrative. Imagine a worm navigating through an apple. It doesn't have to go around the surface. It could burrow straight through the center, creating a hole, hence the term wormhole. But here's the catch. These wormholes aren't just cosmic shortcuts, they're highly unstable. Without something known as exotic matter, which hypothetically has negative energy density, these wormholes could snap shut in an instant. Yes, the universe has a knack for being as fascinating as it is terrifying. In essence, a wormhole isn't just some fantastical concept from a science fiction tale. It's a serious proposition by renowned scientists, grounded in the most profound theories of physics. So, when we're talking about wormholes, we're delving into the very fabric of the universe itself. In theory, a wormhole is like a tunnel with two ends at separate points in space-time. But how does a wormhole work? Let's embark on a journey to demystify this cosmic phenomenon. To comprehend wormholes, we must first understand the fabric of space-time. Imagine space-time as a two-dimensional sheet that's stretched out. All the celestial bodies like stars and planets sit on this sheet and create a dent, much like a heavy ball sitting on a rubber sheet. This dent is what we perceive as gravity. Now, a wormhole, in theory, is a tunnel that can bend this sheet, creating a shortcut through space-time. Consider an apple. For a tiny worm, crawling from one side of the apple to the other would be a long and arduous journey. However, the worm could save time and energy by burrowing a tunnel straight through the apple. This tunnel, in essence, is what we refer to as a wormhole in the context of space-time. It's a hypothetical shortcut through the fabric of space-time, enabling us to traverse vast cosmic distances in a blink. Though wormholes are still a theoretical concept, they are not just a figment of sci-fi imagination. They have roots in one of the most respected theories of physics, Einstein's theory of general relativity. This theory, which describes how gravity works, allows the existence of these peculiar tunnels in the mathematical sense. However, it's important to note that while Einstein's equations permit wormholes, they don't necessarily dictate their existence. We've yet to discover concrete evidence of wormholes in the universe, but that isn't stopping scientists from exploring this exciting concept further. After all, the potential implications for space travel are too significant to ignore. So, wormholes, though not yet proven, are a fascinating concept backed by Einstein's theory of general relativity. They represent one of the many cosmic curiosities that keep us looking up at the stars, wondering what else is out there in the vast expanse of the universe. Tune in next time as we delve into the potential role of wormholes in space travel. Now, how do wormholes relate to space travel? Imagine you're trying to get from one side of a mountain to another. The long way around would be to descend the mountain, cross the valley, and climb the other mountain. But what if there was a tunnel through the mountain that could get you to the other side in no time? That's the idea behind using wormholes for space travel. Wormholes, in the context of space travel, could act as shortcuts through the fabric of space-time. They could potentially allow us to travel faster than light. Now, before you scratch your heads, let's clarify one thing. When we say faster than light, we don't mean breaking the cosmic speed limit set by Albert Einstein's theory of relativity. Instead, we mean that a journey through a wormhole could get you to your destination quicker than light would traveling in normal space. Imagine you have 2 points in space, A and B. In normal circumstances, light, the fastest thing in the universe, would take a certain amount of time to travel from A to B. But with a wormhole, the distance between A and B could be drastically reduced, making the journey much quicker. In essence, wormholes could allow us to traverse vast cosmic distances in the blink of an eye. But before you start packing your bags for a trip to Alpha Centauri, there are a few catches. Wormholes, if they exist, are likely to be extremely unstable. They could close up the moment anything tries to pass through, crushing it in the process. To keep them open, we would need a form of negative energy, something that is purely theoretical at this point. Furthermore, creating or finding a wormhole of a usable size and keeping it stable would require an enormous amount of energy. More energy, in fact, than the output of countless suns. So while the prospect of wormhole travel is fascinating, it's currently firmly in the realm of science fiction. Wormholes, if they exist and can be harnessed, could revolutionize space travel. So, what does this mean for the future of space travel? Let's start by imagining the possibilities. If wormholes are indeed feasible, they could revolutionize our understanding of the universe and our place within it. Picture a future where we could travel light years away in the blink of an eye, a future where the farthest reaches of the cosmos are within our grasp. The implications of such a future are profound, not just for exploration, but for our understanding of life, time, and the universe itself. However, we must remember that the science of wormholes is still in its infancy. There are countless questions yet to be answered and mysteries yet to be unraveled. Theoretical physicists around the world are engrossed in this enigma, conducting experiments, pondering equations, and pushing the boundaries of our knowledge. One of the current areas of investigation is whether wormholes can be stable enough for travel. Some theories suggest that they could collapse instantly, while others propose that exotic matter with negative energy could keep them open. But exotic matter is, in itself, a theoretical concept. Hence, the puzzle of wormholes is like a matryoshka doll, with one enigma nested within another. There's also the challenge of detecting a wormhole. As they are predicted to be microscopic, finding one is akin to searching for a needle in an astronomical haystack. And even if we did locate one, how would we enlarge it, navigate it, or even survive the journey? These questions underscore a crucial point. Our understanding of wormholes is still theoretical. There's a vast expanse of knowledge we have yet to uncover. It's a journey of discovery, filled with challenges, breakthroughs, and perhaps even paradigm shifts. Yet, it's precisely this sense of mystery that fuels our exploration. The pursuit of understanding wormholes is more than a scientific endeavor. It's a testament to human curiosity, a testament to our relentless quest to comprehend the cosmos and our place within it. While the mystery of wormholes remains unsolved, The pursuit of their understanding continues to fuel our curiosity and drive our exploration of the cosmos.